What is up, amigos? Today we're talking about D'Alembert's paradox, and this is a very common paradox in fluid mechanics, and it's been around for quite a few hundred years. So we're talking about what this is and why it comes about, and why actually these days we know that it's not really a paradox, we understand it quite well. So to begin with, let's talk about a cylinder, which we actually went through the potential flow of a few weeks ago in this video. So we understand what really happens over this cylinder. And from that video, we concluded that if you wanted to find the pressure coefficient over this entire cylinder anywhere, it's actually very easy. So Cp equals 1 minus 4 sine theta squared. So this is a very powerful formula that gives us a lot of information about the cylinder. Literally, just by knowing the angle, we can figure out what the pressure coefficient is. And we know that the cylinder, let's say we have a U infinity velocity coming this way. So the angle 0 is here and it goes around anti-clockwise, pi on 2, pi, 3 pi on 2. And if we were to graph the pressure coefficient over this cylinder, so let's just draw this here, where we have Cp up here, and this goes from 1.0 because we know at maximum the sine theta, 1 minus 4 sine theta squared is 1.0, and the minimum is minus 3.0. And at 0, pi is here, and 2 pi is here, so then pi on 2 is here, and 3 pi on 2 is about here. At 0, the pressure coefficient is 1.0, so you can plug that in there, you find that yourself. At pi on 2, it's minus 3.0. At pi, it's 1.0. At 3 pi on 2, it's minus 3.0. And at 2 pi, it's 1.0. So connecting all these, let's just do this graph. This is how the pressure coefficient fluctuates over this entire cylinder. So knowing this, we can actually figure out that the pressure, if we were to cut this cylinder in half, the pressure on top is literally symmetrical to the pressure underneath. The pressure back here at 0 is the exact same as the pressure at pi, which is 1.0. At pi on 2, it's minus 3.0. And anywhere along here, they all cancel out. So that means that the pressure back here is the exact same here, and as we go along. So for lift, we can tell that there is 0 lift, and that makes sense because this cylinder isn't rotating. In last week's video here, we went through when the cylinder was rotating, and that then produces lift. But for a stationary cylinder, there's no lift, and that makes sense. But the drag, this is the important part now. So if the pressures on the upstream phase cancel out with the pressures on the downstream phase, that means the drag and the drag coefficient equal 0. And this is a major problem. This is where D'Alembert's paradox comes into it. So in real life, we know if we put a cylinder in a flow, we do not have a net drag or drag coefficient of 0. But in potential flow, this equation that we got out of it tells us that the drag coefficient and the drag is 0. So what is going on here? This is the paradox. D'Alembert's paradox says in potential flow, there should be 0 drag, but in real life, there isn't 0 drag. So why is this? And for hundreds of years, this fooled fluid mechanists, and they didn't really understand what was going on. But we now know that this is due to viscous effects. So in potential flow, we don't take into account viscosity, and viscosity rears its head in two main ways, one direct and one indirect, that results in there being drag. So the indirect result, let's draw a cylinder again down here with potential flow. So the potential flow says that a streamline coming here, stagnate here, and then there'll be another stagnation point here, and a streamline coming out. And then the rest of the streamlines will come up and over around like this. And over the entire cylinder, the flow is attached. In real life, this is not what happens. We actually have the cylinder here, and as the flow comes along, there might be a stagnation point, but then this flow over here will start to separate at some point at the back here. And this depends on the Reynolds number and the surface roughness, etc. Check out this video if you want to learn more about that. And we get a wake. So this is because viscosity results in the boundary layer forming. And if you don't know about boundary layers, check out this video here. And at a point, the boundary layers will lose steam and they'll separate. So that results in a wake forming. As a result, the pressure on this face back here is no longer the same as the pressure on this face here, and they do not cancel out. We then get a drag forming here. So this viscous effects, these viscosities, that is producing a pressure drag. But there is also a direct effect that is also producing drag, and that is just the viscous effects producing friction drag, because now we have a boundary layer forming that's resisting the movement of the cylinder through the air. So we get a friction drag here as well. So viscosity results in there being pressure drag and friction drag, which means that in real life, because we have viscosity, the drag and drag coefficient are no longer zero. But in potential flow, where there is no viscosity, the drag and drag coefficient are zero. So that is D'Alembert's paradox, and why people thought that there was a paradox to begin with. But we understand now that it's not really a paradox, it's just an emission of viscosity from potential flow. So that's the end of the video. If you liked it, make sure to like and click the subscribe button, and we'll see you tomorrow. Peace, amigos.